The last series test that we want to talk about is the alternating series test. So the first thing we need to do is talk about what are alternating series and then how we can test them. So first of all, alternating series, the terms of them are going to be alternating between plus or minus. One of the things that I want to remind you of is that the harmonic series actually diverges. We know that from the p-series test, but the alternating harmonic series actually converges, and we can see that in the picture of the alternating harmonic series. Now, the alternating series can either diverge or converge. If they converge, they can converge either absolutely or they can converge conditionally. So one of the things that we're going to do is we're going to use a divergence test first to see if that can tell me if it diverges or not. And then we're going to see if it converges absolutely by deciding if the non-alternating series converges or doesn't converge. Notice it doesn't have the plus or minus 1 alternating. And then we can also see if it converges conditionally. To determine if it converges conditionally, we need to make sure that each successive term, the next term, is always smaller than the previous one, as long as it's not increasing in magnitude. And then we also want to check if the limit of the term, not the alternating part, just the term, is equal to 0. So we're always going to start off with this guy right here because this should resemble the divergence test. So let's take a look at example number 1, part A. So notice that we're going to take a look at the non-alternating part, so I'm going to write that over here, is going to be 1 over k squared. So the first thing we're going to do is take the limit of 1 over k squared as k goes to infinity. And we're going to find that's equal to 0. So the divergence test doesn't say it diverges. It says you need to pick another test. So we're going to pick another test. Before we keep on going, what we're going to do is we're going to find if this converges or diverges. Well, from the p-series test, we know that this converges. Because our non-alternating part converges, then we can actually say that our alternating series actually converges absolutely. Let's try the second one. For this series, the first thing we need to do is to determine what is our series. So we're going to see that this is the same thing as something alternating, so that's going to be our negative 1. Notice that if the first term, we just got a positive 2, so I got to make sure I get a positive number, so I'm going to do k plus 1. You can also use k minus 1. Notice, if we take a look at our pattern, that at the bottom we have k, and at the top we have k plus 1. It's always one bigger than the number we put in. So if that's the case, if we look at the non-alternating part, we have k plus 1 over k. So now let's take the limit of just our non-alternating part as k goes to infinity of k plus 1 over k. When we do that, we find that's equal to 1. From the divergence test that says that as long as it doesn't equal to 0, then it must diverge. So we actually find that this one is diverging. That also implies that our alternating series is diverging. Now let's try the last one. If we take a look at the non-alternating part, we're looking at the natural log of k over k. So let's first take the limit as k goes to infinity of the natural log of k over k. When we do that, we're going to find that's equal to 0 by using our growth rates, which means our divergence test is inconclusive and we got to keep going. So the next question is, does this series, the non-alternating part, does this series converge or diverge? So let's see, for this type of problem, maybe we should compare it to something that looks like 1 over k. So we notice that the 1 over k, this is going to be bigger, because even if we plug in k is equal to 5, let's say, I'll have the natural log of 5 over 5, and on this side I'll just have 1 over 5. So this number is bigger than 1, so we're going to have more on this side. So that means that we have our comparison of one series larger than the other. By the comparison test, we're going to find that our series here is diverging. And the reason why it's diverging is that our chosen one that we're going to compare it to, we know actually diverges. And this one is smaller than the other one, so if the small one diverges, then the bigger one must also diverge. Remember, we noticed that this was diverging because of the p-series test. So what we have then is that we have that our absolute part right here is not converging. It's actually diverging. So we cannot say it converges absolutely. So let's see if it converges conditionally. Is to see if the limit of AK is equal to 0. We have that. Then the next question is, are the terms in non-increasing in magnitude as we go along? So if I sit there and I see something that looks like the natural log of 5 over 5, and we compare that to the natural log of 6 over 6, we want to make sure that these terms are actually getting smaller in size. And in fact, we do find that that's what's happening. So because it meets these two, we know that this series converges conditionally by the alternating series test. So let's take a look at some more examples. Let's start with this first one. And let's take the limit of 1 over the square root of k as k goes to infinity, and we're going to find that's equal to 0. So we cannot conclude that it diverges. So the test was inconclusive for the divergence test, but that's okay. The next thing we're going to do is find the infinite series of 1 over the square root of k, and notice that that's the same thing as the infinite series of 1 over k to the 1/2, and we know that this diverges because of the p-series test. Because this diverges, we cannot say it converges absolutely, but because we have this part, all we need to do now is check that as we're going along, that the next term is going to be smaller than the previous term, and we can see that they're constantly getting smaller. Because of that, then we can conclude that this series converges conditionally by the alternating series test. Let's take a look at the next one. Again, we're going to go find the limit as k goes to infinity of 1 over the square root of k cubed, and we can see that that's going to go to 0. Again, an inconclusive test. But that's okay. Let's go find the infinite sum of 1 over k to the 3/2. And what we're going to find here is that this actually converges by the p-series test. If that's the case, if it converges, then we can say that the entire series converges absolutely by the alternating series test. And for the last example, let's take a look at our series. What we notice here is that sine of k will actually go between +1 and -1. So we know it's going to be in those numbers. So let's take the absolute value of that. So we're going to take the limit as k goes to infinity of the absolute value of sine of k over k squared. So notice what I said. This number is going to be some number between -1 and 1, and the one at the bottom is going to be infinity, so that equals to 0. So our test is inconclusive. But that's okay. Let's now look at our series, and we're going to think of sine of k as what's causing it to alternate between positive and negative. So really, we're going to look at 1 over k squared. And when we're looking over 1 over k squared, we know that this converges by using the p-series test. So we don't have to look any further. What we can say then is that our series will converge absolutely. And that concludes this video.